Okay, good. So here is the topic we are going to discuss today. That is basically particle physics. Okay, is that screen shared with you people?
Now it is.
Now it is loaded now. So particle physics and nuclear and particle physics is that topic from which there are at least two MCQs, not at least, almost two MCQs. Yes, it is fixed. Two MCQs and 6 to 8 marks theory question is there. So it is almost 8 to 10% weightage chapter. Got it? So the weightage of this chapter is only 8 to 10%. So uh, this is just the orientation of that. Some of the questions are from particle physics here, and some of the questions are from the basic nuclear, basic atomic physics. Because when we talk about particle physics, I will tell you about that. But starting from the atomic structure, it consists of two parts. One part is your atomic structure, and the second one is your subatomic structure. I mean, particle physics. So let's go to the basic details of your atom. So when we talk about atom, atom comprises of two main parts. One is the nucleus. The second one is its uh, outer shells, which are basically consisting of electrons, or they are also named as orbits. No? So nucleus consists of nucleides, right? This is a new word, yani new term, that the nucleus consists of nucleides, and those nucleides are basically protons and neutrons. So overall, we call it nucleons, right? What do we call them? Nucleons, right? So when we talk about the inner structure, we will study about the protons, neutrons, electrons, and they're all are basically, when we go in detail of that composition of proton and neutron, we will talk about the particle physics, right? So it is just a simple idea about your particle physics, yani atomic structure. In atomic structure, do you people know that in our there are two states of our atom? One is a neutral state and the second one is stable state.
Like as in with the electrons.
Just a second. Hmm, okay. Sorry. Yes, I got some interruption from WhatsApp. Some videos, sorry, some audios were playing, so I thought that someone is talking to me. That's why I was just what is asked to me. Okay, so what I was asking to you, that do you know that there are two states, or two stages, two states of the atom? One is the stable state, and the second one is the neutral state. Hmm?
Is it like when in the neutral state there's an equal number of electrons and protons, and in the stable one there's a full shell of electrons? Is it like
Yeah,
that?
exactly. Neutral state is that state when atom has not mm, made any bond, or I mean, it has not shared or accepted some electrons. Number of protons and number of neutrons are equal in that state. So that is called your neutral state. So atoms does not have net charge. So no net charge over there. So at that stage, number of protons is equals to number of electrons. Got it? Equals to number of electrons. So moving forward, when we have its uh, you know stable state, stable state mean if there is octet completed around the nucleus, yani in the outermost shell. So yes, octet mean it must have 2 or 8 electrons in the outermost shell, at least 2 or at least 8 electrons. So For that purpose, I have shown you this is slide, that in this one, do you see that I mean, here it is basically the nucleide notation. The number of A's, X is the nucleide notation with two symbols Z and A. A is its nucleon number, which is atomic mass, and Z is its proton number. So you people are very much aware of this. So I will not waste much more time here. I will move forward quickly. So number of protons in the nucleus of the atom is Z, right? What are the number of protons? Protons are actually, that is represented by Z. So if I say that, yeah, that I have written it in my notes as well. The number of electrons in the neutral state of the atom is equal to number of protons. So then we have this A. Okay, A is actually number of protons plus number of neutrons. So if I want to calculate number of neutrons, neutrons will be A minus Z. So to somehow it is a quick revision for you. You people can have an idea that okay, we can have we have gone through this in O levels. So there are several uh, atoms of the elements which have same number of protons but different number of neutrons. That leads the idea of isotopes. So I will move forward that in all these, if you subtract uh, Z from A, you will get number of neutrons. So in this way, I have extracted that all. So this is another information slide. In this slide, I have shared the information with you that charge of the electron is E, which is equals to 1.6 exponent minus 19 coulomb, and it is given in the data sheets. This is given to you in the data sheet. This is given to you on in the data sheet, because that is charge of a proton, charge of electron and proton are equal. That is why I can say that if I have an electron and proton, their charge will be just negative and positive, but equal in amount, equal in magnitude. Then mass of a proton, this is relative mass. If you remember, we usually say that 1u, 2u, 3u. So that is mass of one nucleon inside the proton. 1u is also given to you. That is 1.66 into 10 raised power minus 27 kg. And this mass is an average mass of proton and neutron. Along with that, you people are having the mass of proton in your data sheet, and mass of neutron in your data sheet, and mass of electron in your data sheet, right? So that is not a I mean, thing which you have to worry about. Then we will talk about that mass of the electron is 1 by 1840 times that u, which is equals to what, 9.02 into 10 to the power minus 31 kg. So that is also available in your data sheet, so you people can manage that from here. Then we have this topic in detail in our syllabus, that structure of the atom was first described in detail by Rutherford and two of his students. Those were Giger and Marsden. ठीक है ना? So Giger and Marsden was basically the, I mean, students. I am using this word students just to encourage you people that student does not mean that O level, A level students. They were basically PhD students or something like that. Yeah, yeah. Don't worry about that. That at your age they did not do that. They did it in their own age. So Giger and Marsden scattering experiment has a lot of questions in your past paper exams. So I mean, there is a chance of one question from atomic structure and one question from particle. So I can say that it's not 100% that the question will be asked from here, but there is a chance for that. So that I will go through that Giger and Marsden scattering experiment in detail. Actually, in this experiment, what did they do? They just bombarded a gold nucleus. This is a gold nucleus, gold foil, actually, not a nucleus, gold foil with alpha particles. These are the alpha particles, and these alpha particles were tested. Their outcome was just test it at the fluorescent screen here. This all experiment was, it took almost 4 years to perform the experiments, to get the results, to publish the paper. That was actually a thesis like paper which was published after this all. So they received the data that most of the alpha particles approach uh, the front part of uh, this detecting plate or detector sheet. That means that most of the alpha particle pass through. These red ones are most of the alpha particles pass through. The black lines show that some of the alpha particles deflected at large angles, and these green lines show that very few alpha particles were those which bounced back. So I will describe all these three observations in detail. Here is that diagram which describes this all in a perfect way. Okay, got it? So in this diagram, I have explained you that there is an alpha particle source. This gun is just like an alpha particle source, and it is emitting out alpha particles. And these spots are basically the spots which are the observations, right? These are the observations. And there were, yani, this was a movable, yani rotatable source. So they justified these all observations. These are the observations. So in this experiment, I have put it. I have just divided it into two parts. One part, first part will be the observations, and the second part will be the reasons. Right. The observation was most of the alpha particle passed through. This was the observation because they observed that most of the spots were in front of the gold foil. This shows that most of the alpha particle passed through the foil. Now, if I just go through this part here, okay, just a second. Yes, okay, it is fine. Okay, that is fine. Okay, the reason behind that was most of the atom or most of the gold foil was supposed to be empty. Yani, it means that we see the gold foil completely solid, but if the alpha particles are passing through it, it means there are some empty spaces. That shows that atom as a whole is very, yani, low density population. It has very small part which is having some part, yani material inside. Rest all of the part is empty. So here is one detailed discussion about that, yani A level standard discussion about that. The diameter of the atom later on they just uh, yani with the experiments they have described it in the paper that the diameter of the atom was almost 10 power minus 10, and in some of the books 10 power minus 10 is said to be 1 angstrom. 10 power minus 1, sorry, 10 power minus 10 is equal to 1 angstrom. So that is estimation, and this estimation, yani in your AS level, this question is also asked. It is not mandatory that it would be asked in your nuclear part or particle physics part. That can be asked to you in your uh, estimation part of the question. First chapter, yani chapter number 1 question. Okay, so diameter of the atom is in 10 power minus 10, but diameter of the nucleus is 10 power minus 15. So 10 power minus 15 means it is 10,000 times, sorry, 100,000 times smaller than its surrounding. Do you get it? That what does it mean by 100,000 times smaller? If I am living in a city and I have only one home in my city, only one. it would not be definitely city, but that would be the empty space around me. Yani 10,000 times space as compared to that of my home, it would be free then. Yani in case of diameter. But when I compare it in terms of volume, because in one of the past paper I have seen this question, so you can calculate the density of the atom in this way, and density of the nucleus. I will address that as that area as well. So volume of the atom will be equal to, because both are considered as spherical. So volume of the atom is what? 4 by 3 pi r cube. Okay. So I believe that you people are aware of the game of diameter and radius, because diameter and radius are uh, they have power 3, so no issue at all. So if I just put it that 4 by 3, 4 by 3, that would be gone. So radius of the atom divided by radius of the nucleus whole cube. So here is this uh, link, that volume of the atom divided by volume of the nucleus, volume of the atom divided by volume of the nucleus is radius of the atom or diameter of the atom divided by diameter of the diameter of the nucleus. So when you put all the numbers here, it is what? 10 power 15. So now you can say that volumetrically nucleus is very, 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 very small. देखो, ये 10 power 15 is, I mean, 100 tera times, na? Can I say 100 into 10 raised power 12 is basically 10 power 15. So what will be that? Yani 1000 tera. Sorry. So it is very big difference. That's why usually the people say that atom is, yani nucleus is so small that if you place a small bead of any bean in the football field, then the comparative uh, volumetric space is the space in the atom and the nucleus. So is this um, concept clear to you, that why they gave you this detail, that the atom is so small that its size, yani nucleus is, yani all the atom was considered to be empty?
Yeah, it's clear.
Okay, very good. The second area is that some of the alpha particles pass through. When it is said that some of the alpha particle pass through, sorry, some of the alpha particles were deflected at large angles. This was the second observation, and this second observation was made on definitely uh, some reasons, and the reason was they proved this logically or with their database that alpha particles were definitely alpha. It was known that alpha particles were positively charged because they are that was ionized helium. So if we consider the logic of electrostatics, alpha particles are positively charged. That's why they are repelled by uh, an entity which would be positively charged. Yani, if it would have a like charge, then they will be repelled, isn't it? ऐसा ही होगा
Yeah.
ना? So if alpha particles are having positive charge and they are repelled, it means the object or the entity which is repelling them, it is also positively charged. That showed that the nucleus is positively charged, right? Our nucleus has something positively charged inside. I mean, it's not that nucleus has positive charge, but nucleus has something which is positively charged. And later on, we found that okay, protons are residing inside. Second thing, which uh, supports the deflection, that is the mass of the that positive part of the atom, that is very high as compared to that of the alpha particle, right? Why? Listen, if alpha particle, yani if the mass of the nucleus would be smaller than alpha particle, then what do you think? Due to repulsion, nucleus should be knocked out of the atom, na? Is it?
Yeah.
Because alpha particle has kinetic energy, alpha particle have repulsion force, So nucleus must be knocked out. But this observation showed, nucleus has very huge mass inside. That is why it deflects the alpha particle in spite of its kinetic energy and its repulsive forces. So from this observation, they made two inferences that the central part of the atom, which was called nucleus, that is very small, uh, as well as it is it contains all of the mass inside, and it is positively charged. Okay. Small is basically not uh, observed, yani that does not support from this inference. Small will be supported from another one, at which I'm just moving on. Okay, that is I have explained the structure here. If you people can understand this, check this one out. I have shown that if that blue atom, I mean this part, this is the nucleus. So if it is big in size, yeah, sorry, big in mass, then it would not be knocked out. It will basically deflect the small positive charge, right? That is why there are some questions in which you have to figure out that which demonstration is correct. So for that purpose, I will just recommend you one thing, that those lines which are closer to, just I have drawn some others. No, those lines, yani those rays, to somehow you can say these rays, which would be closer to the nucleus, they would deflect at larger angles. Yani I'm just going to draw this. For example, this is the nucleus, right? And you people will be given some sort of these type of rays. So if this is the ray which is closer, it would deflect more. And if there is another ray which is a bit above, its deflection will be less, right? So these type of deflection you have to mention, and you have to take care of it, that those alpha particles, these lines are these rays shows the path of alpha particle. So those alpha particles which would be incident closer to the nucleus, they will deflect more. So if you say this alpha particle would have more deflection, this alpha particle will have more deflection, and you see here that is coming closer to the nucleus. That's why it is repelled more strongly. Got it? Anilal. Clear? Any confusion in this one?
No conclusion.
No.
Okay, so here I have just explained, I think, on demand of a student, that neutrons and protons in gold its gold's new proton number is 79, and its uh, nucleon number is 197. So it means the total mass of the nucleus of the gold is almost 3.27 exponent minus 25 kgs. We can consider it, although it is very small in 10 power minus 25 kg, but it is much more than that of alpha particles. Is it? You can roughly say that it is 197 times, yani 200 times massive than that of the alpha particle. No, 200 times, because alpha particles have 4 U's and it has one, yani 200 U's, so 50 times almost. Got it?
Yes.
Okay, go back to the point. Okay, yes, I was talking about you that there is a question of density, of the calculation of the density of the nucleus and density of the atom. So go, yani mass of the atom is equals to what? Mass of nucleus and plus mass of the electrons, plus mass of the electrons. It is plus sign. Okay, so here I have corrected that one. So I have calculated that. After all these calculations, you came to know that mass of the atom is actually equal to how much? That is sum of these two numbers. So when we add these two numbers, we get 3.2 into 10 raised power 27. It's very simple. There are 79 nucleons. Sorry, 179 nucleon. It would be given to you, right? It will be given to you that we have 79 nucleons, 179 nucleons and 79 electrons. 197. है ना वो? है ना, Aban? Was it 197? Sorry.
It was, I think
Yeah,
so.
197. 197. Sorry. So it would be given to you in this way: 79 and 197. Right? Yeah, it can be of any atom. It is not that you will be given for the gold. It can be for any of the atoms. Is it clear?
Yes.
So just a second. My charging plug is having a problem. Okay, now it is fine. So mass of the atom is given to you, and mass of the atom is almost 3.2 into 10 to the power minus 25 kg. And density of the atom, it is density of atom, right? Because mass is density is mass by volume, so it is actually equal to this number. So when you will place these all values inside, you will get density. Just a second. Okay, I was taking water. So back. Yes, check this one out. Density is mass by volume, and if I say instead of calculating volume of the nucleus and atom again, I have given you this idea that density of nucleus divided by density of atom is mass of the nucleus divided by mass of the atom, and volume of the atom divided by volume of the nucleus, because density is inversely proportional to volume. That's why. So I have given you the ratio of volumes in the previous discussion, and masses we have calculated. So it's immense uh, idea that atom is almost 10 power 14, yet 10 power 15 times denser. So nucleus is 10 power 15 times denser than that of atom. You got it? Because mass does not make a big difference. Did you see? The only game is of this ratio, because that ratio was almost 10 power 15. Na? We have calculated that in the previous discussion. है ना?
Yes.
So that mass is, that ratio is the yani difference creator. So this is how we calculate everything for the atom. Now this is the third aspect. The third aspect is that yani that was the third observation. They made this observation that very small number of alpha particles were bounced back. Yani this was their observation at larger angles greater than 90. So this is a beam of alpha particle. This entire is basically what? A beam of alpha particle. So if I have a beam of alpha particles, and those alpha particles are actually stuck by, or they are bounced back by the atoms, yani nucleus inside. If the size of the nucleus is equal to size of nucleus 1, only 2 would be deflected. Is it? Do you see that? If the gold nucleus is this much big, how many would be deflected? All in this range. So they are almost 4 5. If the nucleus size is this much, more would be deflected. This much more would be deflected. This much more would be deflected. So in this way, if we go conversely, yani back from top to bottom, so why they were very small deflected? Because the size of the nucleus was very small. Is it? So if it would be big enough, more would be the particles which would not be able to reach the nucleus, so they would repel. Is it clear? So the conclusion is
Yes.
atom is empty space, mostly atom is there. So these are the five inferences coming from these all observations. The nucleus is in the center of the atom. Nucleus occupies almost all of the mass of the atom. Nucleus is very small in size and nucleus has positive charge inside. So I believe that you people have this concept very clear. If there is something which is not clear to you, you people can ask me. There is a question I have noticed from this part that, you know, because alpha particle is not touching its, yani alpha particle could not uh, touch the nucleus, right? So alpha particle would have some kinetic energy when it would be fired. And for example, we say that alpha particle is at rest over here. Here its velocity is u, and here its velocity is v, and v is equal to 0, or not 0, but it would be small enough because of repulsive forces. If it is not 0, it's fine. So change in kinetic energy is equals to work done against repulsive forces. Okay, are you getting? So this is a aspect which can be asked to you. Work done against repulsive forces. So you can be given with repulsive force. For example, it is 1 by 2 m v square minus 1 by 2 m u square. That is change in kinetic energy, and that can be equal to F into d. For example, you can be given that how much distance will it cover, or if distance is given to you, how much speed would be left over, or how much speed would be remaining. That's it. These type of questions are asked from this topic. Is this all clear to you?
Yeah, it's clear.
Okay. Right after that, this is the topic of nuclear radiations. I will try to finish this up because this is again some sort of revision for you. So it is not a big challenge for you to recall it. I think that you will not be burdenized if I consider this. So nuclear radiations are basically of uh, those nucleus or those nuclei which are heavy enough. Heavy means they have the atomic number greater than 80, Z greater than 80. They are considered as unstable. Unstable mean they are they radiate some sort of energies, particles spontaneously. And if we bombard their nucleus, they are decayed easily and they are not stable. So in your A levels too, I will let you know that most stable element is your iron. So all the elements whose atomic mass is yani Z is less than iron, they are unstable as well, but they are not considered to be highly unstable. They fuse together to get stability, yani they merge together, so that generates the fusion reaction. And those all which are having the mass greater than 56, they are considered heavy elements, and they disintegrate to get stable, and they just release their load to get stable. And those one which are lighter one, they get some load to get stable. So that is a another discussion. I will not get indulged in that one. In that is in A levels too, so I would be just focusing on my topic. So here the game is the game of binding energy. Again, I will tell you that binding energy per nucleon is your A levels 2 topic. So I will discuss that in that class, inshallah, in detail. Uh, there are some sort of calculations at the end. I will discuss those calculations. I will discuss that area of the calculation with you. Rapidly, I would wind up this that radioactivity is that process in which the radiations are emitted, and there are three types of radiations you have considered: alpha particles, beta particles, and gamma rays. Is it? So these three type of radiations are basically the radiations which are there coming from the nucleus of an unstable, unstable atom. So there are some specks of alpha particles. I believe that they are known to you, that they are helium nucleus. They have +2 charge. They have 4 U mass. So I told you what is E and what is U. So +2 E means 2 times charge of an electron or charge of a proton, and 4 U means 4 times mass of 1 U. 4 times mass of 1 U means 4 into 1.66 into 10 to the power minus 27 kg. So they have strong ionization. They have very small penetration power, very small. They can be blocked by at least 10 centimeter of air, or they can be blocked by a paper. So that shows that they have very small penetration power. Then they have the deflection in electric field and magnetic field both. In electric field, they are deflected towards negative plate because they are negative positively charged, so definitely they would go to positive plate. And in magnetic field, they are deflected perpendicular to the magnetic field, but they follow Fleming's left hand rule. I believe that you people are aware of that rule. I should explain it in this way. Point your hand into the magnet, into the page, left hand, and your finger should be split at 90 degree. Your index finger should be pointing in the direction of magnetic field, and your middle finger should be pointing in the direction of the particle motion, and thumb will show its deflection. So if you apply that rule here, you will be able to understand it. Can you try it, please?
Yeah.
Yeah,
Okay.
is it clear?
And the
Okay.
direction of like
So,
the like
yeah, if it would be a beta alpha particle, because I'm talking about alpha particle, so you will use
yeah.
left hand rule. But if it would be a beta particle, I will talk about that beta particle, then that particle would have to be applied by the other, because there are two types of beta particles. We will discuss about that. उसी पे आके फिर discussion करते हैं beta particle. Then this is that I have explained. I tried my best to explain this. I believe that you will not mind that diagram. ठीक है? mean Artistic approach is not good. That's why it was just to make you clear. Now we will talk about beta particles. Beta particles are basically result of weak interactions. This is an MCQ, what I have addressed here, that what is the main reason of beta particles. So weak nuclear forces are weak interactions. So there are two types of beta particles. I will talk about that in detail in particle physics, because these two are the part of the particle physics. So here I will just talk about them just like a radiation, not as a particle. Okay. So so radiation beta particles, they are called positive beta particles, are considered as positron in the particle physics. Again, I'm telling you, in the particle physics they are considered as positron, and in the particle physics they are considered as electron. But here we will talk about them, that beta radiations are beta particles. So if there is the positron, its symbol would be +1 e and 0, or plus beta and 0, or it would be plus e, its charge is +1 e. If it would be a negative beta particle, it would be represented by the symbol of electron, -1 e and 0, or -1 b and 0, and it has the -1 charge. That's it. Ionization power is comparatively less than that of alpha, but more than gamma. Penetration is comparatively more than alpha, but less than gamma. And they can be blocked by at least 5 millimeter aluminum sheet. They can be blocked by 5 millimeter aluminum sheet. So deflection is more than alpha particle in both the fields, electric and magnetic. So in electric field, if there would be positive beta particle, they will deflect towards negative plate, but more than alpha. देखो, alpha is this one, green one. So beta's deflection is more. And if there would be negative beta particle, they will deflect it towards positive plate, but with more deflection. Is it clear?
Yes, it's clear.
Okay, yeah, are you there in the class?
Yes, I am.
Okay, very good. So deflection comparison is here. I believe that this diagram will be very clear to you. For positive beta, you will use the left hand rule. I mean, they would be in the same direction as that of the alpha particle, but more deflection. For negative beta, deflection will be opposite, but equal in magnitude of that of the positive beta. So here is the diagram which shows all of these three deflections, and gamma will have no deflection. So I have just a small discussion about the gamma. So gamma radiations are basically the radiations, photons. This is asked to you, what are the gamma rays? Those the gamma rays are actually electromagnetic photons. Okay, electromagnetic photons. Remember this sentence. They are of different colors. They are of different frequencies. They have no charge, no mass. They have almost no ionization energy, but they are very dangerous from outside the subject, but not from the inside the subject. And secondly, they have no charge, no mass, so they have no deflection, but their penetration is infinitely large. They can even cross the lead blocks, but by thick lead walls, we can block them. So this was just an effort to represent the penetration strength of these particles. Alpha particles are blocked by a paper, beta particles are blocked by aluminum sheet, and gamma radiations are slowed down by lead sheet. And if we will make thick lead, maybe they would be blocked. Got it? And their speed is same as the speed of light. So that's why, but they're highly energetic than that of light. This is very dangerous aspect, that they are as fast as light, but they are highly, yani thousands of times, I mean, not thousand, trillions of times more energetic than that of light. So we will discuss that in the next part of my lesson with calculations, inshallah. So is this all clear?
Yes,
Yes, sir.
it's clear.
Any confusion or anything you want to ask me?
No.
No?
Nothing. Actually, I tried to fulfill my promise that in 2 lessons I will wind it up. This lesson was not new for you. That's